So, public pools.
Public pools. We will start with a short review of combined chlorine and THMs. Then we'll talk about the 4 ways of treating public pools.
Then we will talk in detail about UV, medium pressure, low pressure, medium pressure, and last but not least, you know, this is really world new in this pool market, advanced oxidation, and yeah.
Yep. Exactly.
Right, stands for innovation, and you will see. It's good.
Yes.
Very good.
And as always, we will take your questions at the end. You can place this. Please use the chat function for this, and we will answer those questions at the end of the session. As always, also you will be able to review the replays on our website. They're available there for 1 week.
1 week.
You will find the program as well and the PowerPoint slides here in a PDF format.
Very well done. You do it each time better.
Good.
By the way, what we also will do in the coming days, Laura is now not here, but in the coming days, we will upload all the sessions to our YouTube channel. We will announce this on LinkedIn, I guess. So check out in the next 7 days, definitely on our YouTube channel, you will find all the sessions in all the languages. Yeah. Okay, let's start with what we are talking about, chloroform. We talked about this before.
Yes, we did. And we want to revisit the 2 most important disinfection byproducts.
Yeah.
Huh? First one,
chloroform.
Chloroform, right? How are chloroforms being formed? You remember this slide from session 4, I believe it was, right? So we form chloroform by breaking down large organics. Chlorine breaks down large organics into its smallest molecule or smallest components, which are methanes, 1 carbon and 4 hydrogen atoms. They will then continue to react with chlorine. There's this substitution reaction that we were also talking about to form monochloramine, dichloramine, and trichloramine, which ultimately...
Chlorine. Chloromethane, dichloromethane. This is why I'm assisting here. Chloroform.
It's still early, right? So we're forming chloroform, which gases out of the water.
Henry constant 185.
Yes.
Yeah, not good. So you heard about this. You heard about this different times. We are really brainwashing you here because it's really important.
Yep.
And what does it mean? If you reduce more organics by better filtration, talking about AFM, if you reduce 50% more organics, you have 50% less of chloroform or other THMs. So here really AFM brings such a big value in, and chloroform is important.
Okay. Yep.
Next.
So the second disinfection byproduct we were talking about was trichloramines. How are they being formed? How do they get into the pool?
Yeah, if you use a pool, you excrete a certain amount of urine and sweat. You see here 50 and 200 milliliters. These are average numbers. There are people who do more, others who do less. But really,
I sweat more.
Yeah, exactly. But the really important point on the urea.
Yes.
80% of sweat and urine is urea. It's organic. It has a carbon in it, and 10% is ammonia. Okay.
Yep.
Forget about the others, not important. Now, we have this biological conversion of urea to ammonia. In this process, you know, to say it easy, it's they eat it and they excrete ammonia. So if you have sand, if you have biofilm, you will convert this 80% of urea to 80% of ammonia, and you start already with 10. So you end up with, I do it black and white. Reality is not, it's a lot more like gray, but I do it black and white. You know, if you have sand, you end up with 0 urea and 90% of ammonia. If you have a bioresistant filter media like AFM, you stay with 80% urea, 10% of ammonia.
Yep.
And the problem with the ammonia is reacting then.
So now is my monodi and trichloramine.
Yes,
okay, so ammonia reacts with chlorine to form first a monochloramine, then continues to form a dichloramine, and then a trichloramine, which has a Henry constant of 435,
yes,
I believe.
Yeah.
Yes,
well done.
Which means it easily gases out of the water.
Yeah. And these monodi and trichloramines, this is why we call them inorganic combined chlorine. We see later on the organic combined chlorine. Yep. And, you know, the trichloramine gas is out, chloroform gas is out, and this is not good.
Yep.
Maybe I take the lead here.
So,
yeah, here you see no biofilm, no trichloramine, because the urea will stay urea. Mm-hmm. But again, you know, this, it's really from a health point of view, it's this toxic, volatile disinfection byproducts are toxic because we breathe them in, they go into our lungs, and this is not good. Trichloramine, if you have high concentrations of trichloramine over a certain period of time, you get asthma. That's not what we want. And chloroform is even worse. It goes through your lungs, in your bloodstream, and damages your nerve system. And this is really not good, not for anybody, but especially not for babies and not for pregnant women, especially the chloroform. So yeah, not good. So why do we talk about all this? I mean, we have seen with AFM, we have a great solution to reduce chloroforms. Very good solution. But what about combined chlorine? Now, let's go quickly back, you know, about chlorine. You remember the DPD measurements, the lobby bond measurements. With DPD1, you measure free chlorine. If you add on this DPD1, DPD3, you get DPD4. And DPD4 measures the total chlorine. And the difference between the free chlorine and the total chlorine is the combined chlorine. This is what we do with the photometers. Mm-hmm. Now, the next thing that we already mentioned it, you have two kinds of combined chlorine. You have inorganic combined chlorine, which is monodi and trichloramine, and you have organochloramine. Organochloramine is formed if you have urea together with chlorine, you form organic chloramines. And I think the key one, the takeaway you should take from here is with AFM, urea stays urea. So you will end up 90 to 80% of your total combined chlorine, the reading that you will get will be organic chloramines, and about 10 to 20% will be inorganic. Again, these are much less toxic than these ones. In a sand filter, it's just the opposite. 80 to 90%, because you convert all the urea into ammonia, you end up with inorganic chloramines, and only 20 to 10% are organic chloramines. This is from a health point of view, that's a kind of importance, but not, you know, from a legislation point of view. In the legislation point of view, they measure the total combined chlorine, and they do this with DPD1 and DPD3. Mm-hmm. And they say total combined chlorine has to be in Switzerland, Germany, below 0.2. Italy, I think it's below 0.4. Same France. Other countries are higher. So for us, with AFM, again, we cannot promise that you have less total combined chlorine. We can promise you have much less of inorganic, but not less of organic chloramines. Yeah, it will be about the same. Can even a little bit higher, because these organic chloramines, they are not volatile at all. So that means we have to solve that problems, because in total combined chlorine, you know, with the Dyson system, you will end up roughly 0.4 total combined chlorine in indoor pools.
So really, the regulators, they don't care if it's inorganic or organic chloramine. No. They just look at combined chlorine, and that's it.
Yeah, yeah. And why is this? You know, these DPD3 measurements, actually, they are older than you are. Can you believe that?
45 years old?
Yes. No, there were we have this DPD measurement since 1957.
Okay.
So yeah, it's it's more than
very
60
old.
Years old. It's good. It's not bad accurate. There would be better solution, but it's very easy. It's very cheap. Everybody uses it, and this is why it's the industry standard. You could measure monochloramine and take this as an indicator, but however, it's not helping us. Again, AFM is a good solution for trialomethanes, chloroform, but it's not a problem solver to reduce combined chlorine. So therefore, we have to do other things. Let's start first with outdoor pools. You know, in outdoor pools, you will have never a problem with combined chlorine. Never. Why?
Well, it's that sun up there, huh? On the chart. So the sun is the biggest UV lamp you can get, huh?
Yeah, you can't get it bigger. That's really powerful UV unit, which will create free radicals in the pools and will oxidize the combined chlorine. Inorganic, organic, doesn't matter. And if you add some ACO, you amplify this process. So no need to do anything else. So you don't need ozone, you don't need UV, to use UV in an outdoor pool is completely senseless.
Don't need carbon, nothing, huh?
Yeah.
For outdoor pools. That's easy.
Yeah.
That's an easy one. Huh?
But again, often you see UV on an outdoor pool. This is completely makes no sense. I mean, commercially, maybe you sell something. We are not against selling. And here is one of the example, pool which is 6 years old in the meantime, Heiden in Switzerland, 25-meter pool. Here it doesn't look busy, but in summertime it's really busy. And just to give you here an indication here, chlorgebunden, that means combined chlorine, this is in German, I apologize for this. They have 3 different systems, and you see combined chlorine 0.05, 0.09, 0.05, so below 0.1. And of course, if it's cold and they don't have any uses, it's easy to achieve. But this was really in August when it was 35 degrees outside, and you also see the water temperature, 26 degrees. So it was very, very loaded. So perfectly, just AFM, APF, ACO, nothing else. And you see combined chlorine really low, THMs 25, which is good for outdoor pools. Indoor, we need to go to 20. Outdoor pools up to, we can go up to 50. Why is this, by the way?
THMs up to
50.
50
are allowed, at least in Switzerland. Yeah, why is this? Because you're in an open system. So volatile, you have wind, the volatile disinfection products are not so good. So you see, I still can learn him something. That's good.
Good.
Turbidity below 0.1, and they also had good savings in chlorine and no chlorine smell, etc. But what's the takeaway? The takeaway is outdoor pools, Daisy is good, is enough. That's a statement for all the people who can read German. This is the summary. He's very happy with daisies. Uli Frick, thank you, Uli. Uli Frick from Heiden, Switzerland. Huh? So, yeah. Okay, let's come to indoor pool. What's the difference in indoor pools? What are we missing?
Well, now we are in a closed building, huh? So we are missing the sun.
Exactly. And again, if you have now a daisy system, AFM, APF, normal daisy system for indoor pools, you will achieve around 0.4, below 0.4 combined chlorine. But if you want to reach below 0.2, which is the legislation again, Switzerland, Germany, Austria, you have to do something. You will not achieve this just with AFM. And what are our solutions? We have 3 different solutions.
So one solution is the addition of a very shallow layer of activated carbon, which is also something that we had discussed in, I forgot, session 4, maybe also 10 centimeters of activated carbon on top of the AFM filter bed will reduce the combined chlorine to
below 0.2.
Below 0.2.
Yeah. Yep. And I know we have talked about this, a little bit of summary, just 10 centimeters. As long as you have chlorine or any other oxidants in the water, you will form on the surface of the carbon, you will form free radicals, and they are really breaking up these combined chlorine, the organic chloramine and the inorganic combined chlorine. If you go with a big layer, so here it's not the more the better. If you go with a big layer, after 20 centimeters, you lost all your oxidation. And then you have no oxidants anymore here. You do not form any more free radicals. The carbon becomes like a sponge.
Sponge, yeah.
Where the organics which are coming through are absorbed. They go into the pores, and then you form biofouling. And this is not what we want. So 10 centimeters is enough. We want to have still a little bit of chlorine, below this. Also, if you only do a 10 centimeters layer, you lose maybe 50% of the chlorine, roughly. Depends a little bit on the flow rate, etc., but roughly 50%. We do not want to lose 100%. So this is the solution to do it.
Yep.
Good. I take today a little bit. It's my favorite subject. I apologize, Philip. You can do it then more in the US version.
Yeah.
Don't use anthracite N. Anthracite N has no absorption capacity. You can't use this. This is really just for room filtration. So completely out of senseless in an indoor pool. Debatable, or yeah, you could use it in an outdoor pool, you know, to have a little bit less of backwashing. I mean, less frequency, this you could do, but really not in indoor pools. What you can use, what they use very often in Germany and in Austria, is anthracite H. Remember, here the surface is only 300 square meters per gram. Activated carbon is 3 times more, it's 1000. Therefore, you need here not 10 centimeters, you would need 30 centimeters. We suggest don't use anthracite H. It can contain iron, you need 300 millimeter layer, so we are not a fan of it. We think activated carbon is cheaper, it's the better solution, you need less.
Yep.
Huh? Okay, what's next?
So that was option 1, right?
That was option 1.
The use of activated carbon on top of AFM.
It is our preferred option until today.
Yep. Okay. Option 2
until today, 9:30. 10:30 will look different.
Yes, exactly. So option 2 to reduce combined chlorine is the use of ozone.
Yes. So use of ozone system, which are very expensive. They're very good. You have AFM filter or a sand filter, then you ozonate the water with 1 gram per cubic meters of water that you treat. So if you have 100 cubic meters of turnover, you have to install here a 100 gram ozonization system. Cost roughly 100,000 euros. So it's quite expensive. You have to go in a contact in a reaction tank and let react the ozone for at least 3 minutes, and then you have to remove it with carbon. And here you need a higher layer of carbon. You know, according to DIN, you need 60 centimeters. Switzerland also goes for 60 centimeters. My personal my personal belief or my learning is that's too much. 20 would be okay. If you want to go on the very safe side, 30, but I would not go to 60. Again, same problem. You will lose all your ozone, and beyond this, you get biofouling problem. You know, the key one is that at the entry of the pool, your ozone level should be not more than 0.05 ppm. But it's a good solution. It's a very expensive solution. It will give really good water quality on the THM values as well as on the combined chlorine values. There is a little bit of risk of biofouling of the carbon, especially if you have too much of carbon, but it's very costly. It's very costly. So yeah, good solution. And you also can leave this filter out and just make ozonization reaction tank and then activate the carbon. That's a little bit cheaper one, but it's really, the costs are here, the ozonization system.
Yeah. Okay.
And also, you know, if that's 100,000, you have to calculate roughly 10% of costs for
operating
service, cost, replacement of the lamps, etc. So yeah, it's a good one. And in Switzerland, our specifiers, Reto, probably he will be on the next call. He loves it. Most of our specifiers are loving it. It's a good solution. We are not against.
Okay.
Number 3, you take this.
Yes. So option 3, we have to reduce combined chlorine is the use of a medium pressure UV. Again, in combination with coagulation, flocculation, and AFM filtration, UV is very effective at reducing combined chlorine. Yes. We know that.
But there are a great job in reducing combined chlorine.
Exactly. But there are some side effects.
Yeah, what's big? But it will increase THMs, chloroform. And this is not good. This is not what we want. And this is why we are against. And I guess we are not making now big friends in the UV industry. Yeah, it's just the truth. Let's explain, you know, a little bit what's behind. Shall I take this, or you want to take that?
Well, what we see is the black line is, you know, the curve for a low pressure UV that peaks at 254 nanometers, I believe.
So that's the wavelength from a low pressure UV.
Exactly.
And this is the wavelength from a medium pressure, which goes from 300 nanometer to 200 nanometer. And here you are between 260 and 250.
And then the colored lines are the lines for different types of chlorine.
Just concentrate here on the red, which is the hypochlorous acid. This is really the effective chlorine. And you see here a point. And at this point, the hypochlorous acid, the chlorine is consumed roughly 50%. If you go through a UV medium pressure, you lose 50% of the chlorine. The other things that we can learn is, if you look at this curve and the black curve, it's absolutely clear that UV medium pressure needs 5 to 10 times more energy than for low pressure. So you consume much more chlorine than you do with a low pressure. You consume a lot more energy. So why do we use medium pressure?
I guess if you look at this, you would say only use low pressure, right? But we're using medium pressure because of the next slide, which has to do with combined chlorine, right? So UV medium pressure, we see this here on the graph, the three color, the green, red, and black. The green is
trichloramine.
That's the trichloramine, the red is dichloramine, and the black is monochloramine. And we can see that medium pressure is much better, much more effective at reducing combined chlorine than low pressure.
So these are the absorption points. Here is trichloramine absorbed at 230 nanometers. Here is dichloramine absorbed at 220, and here monochloramine at 210. And you see with a low pressure, it makes nothing, or nearly nothing. So really here is the work. So to break up inorganic combined chlorine, you need medium pressure. I mean, there is no, forget low pressure, will not work. It will reduce less of chlorine, yes, much less, maybe under 10%, where the UV medium pressure will consume 50%, but it does not the job to break up inorganic combined chlorine. It has an effect on organochloramine, because organochloramine, I don't know exactly where it is, but it's somewhere around here or here. It has some effect on organic combined chlorine. We have seen reduction of 25%. UV medium pressure would be also more effective in this because it's just a much higher wavelength. So to summarize, UV medium pressure really makes a good job, will reduce the combined chlorine, inorganic and organochloramine by 50%. Low pressure makes nothing with inorganic, makes about 25% if it's a well-sized system on organic or chloramine. So that means really, if you want to treat your water full stream with UV, you have to go for medium pressure with much higher power consumption, and you treat the full stream.
But then again, there are some downsides to it. So one is that the combined chlorine is oxidized into nitrate.
This is what you see here. The medium pressure, you reduce inorganic combined chlorine by photolysis. This is the process. These photons split this up. Monodi and trichloramine is oxidized to nitrate. This is the formula that you see here. And nitrate is
a food source. It's a fertilizer.
Fertilizer.
For algae, bacteria.
It's great for algae and for bacteria. But our main point is this photolysis, these photons which break up these inorganic and organic combined chlorine, they also break up big organic molecules in smaller ones. And the smallest one that we end is 1 carbon 4 hydrogen. It's a methane. And that reacts then with chlorine to form chloroform. And this is why we are against. We have nothing against the UV industry, but this is why we are against. Was this clear enough?
Yeah, I think so.
Okay. If you have one, or if you're a believer, and a lover, if you're a lover, not a fighter, if you're a lover of UV medium pressure, and you say, Dominic, this is Dominic and Philip, we want to stay with this, or we have installed, we don't want to change. There is one thing you can do. You could dose 1 milliliter of ACO per cubic meters of treated water. So again, if you have 100 cubic meters per hour of turnover rate,
Yeah.
medium pressure, you could dose just in front of your UV medium pressure, you could dose 100 milliliter of ACO.
Mm-hmm.
And what it does, you see here, the black line is UV without ACO. And you see it goes here up to, I don't know what it is, I guess it's 100% of this short wavelength, 350, 250 and below. If you add ACO, it will, maybe you explained this, your English is better, deflect.
Deflect, yes. So you change the shorter wavelengths into a longer wavelength,
yeah,
which are less destructive, if you will.
Yeah. And by this, then you release some energy. Mm-hmm. And this energy has the potential to spread water molecules into free radicals. So you produce some free radicals. Mm-hmm. Not huge, but roughly you produce some free radicals which jump up, which make complete oxidation. So you reduce your THM's level roughly by 20%. This you see here. Yep. It's roughly at 20%. Yep. So yep. If you dose ACO in front of UV, and we test this out in England, we test this out in America. In America, you have really exciting, but I would promise about 20% less of THMs. Mm-hmm. Mm-hmm. And that's important, that's significant. Huh? So, summary. You're good in summarizing.
Okay, so summary. UV medium pressure causes photolysis of not just combined chlorine, but also of chlorine and of organic substances. Huh? The short wavelength,
this is the red line here.
Exactly, yeah. Is what breaks down the organics into smaller particles, smaller parts, components, which then will react with chlorine to form chloroform.
Yeah.
So that's a very important process to understand.
Yeah, and this is why we are against. Read the red line. This is why we are against.
Yeah. Then in addition, inorganic chloramines will form nitrate when they're oxidized. So this is a food source for algae and bacteria.
That's also a point. But the important point is the red one. We don't want to have these THMs. Yeah. So if you have it, that's the green line. If you really want to do it, use some ACO, then the problem is much less.
Yep.
Okay, Bad Hesselingen, this is, and thanks to my friend from Pomats, Hank, Roy, and all the great people there, because they are responsible that we have here in Bad Hesselingen in Netherlands, we can use this as a test pool. It's a 25-meter pool, it's 5,500 visitors per week, so really busy. And we made there a lot of tests. Why have we done them there? Because it's much cheaper than in Switzerland. What did we test? Or what Thomas did test. For 2 months, we had the old situation, which was flocculation with sand. And then we changed this to AFM and APF, and we tested it for 7 months. Then on top, we added UV. In this case, it was a low pressure, to be fair, which works with organochloramine. Not that great as medium pressure, but it works. And then we stopped the UV and added a 10 centimeters layer of carbon. And we tested this, they tested it once per month, always the same day, same time, to have more or less equal parameters. And it was done by CMARC, which is probably the best lab that you find. Philip, what did we test?
Okay, so we tested, I think, 36 parameters: turbidity, pH, free chlorine, total combined, and so KMNO4, urea, temperature, and then the biology I cannot spell.
So the all these animals that we will talk in the next session. Also chlorate, THMs, trichloramine in the air. Not every month, but in some months we did. So, I mean, you can't do bigger tests. Each of these tests was 1,000 euros. Again, in Switzerland, that would probably be 5,000 euros. This is why we did it in Netherlands. So here are the results. Stage 0, that was with sand. You see, combined chlorine was 0.6. And KMNO4, remember KMNO4, that's the oxidability. This is the measurement for organic load was, let's say, between 8 to 12, 10, let's say in average. Then we changed to AFM, and you see here 0.4, 0.4, 0.4, all good, and which is a reduction of 50% that we do not promise. In this case, it was a reduction. KMNO4, the organic load was roughly 50% of what we had here before. And here you see some red numbers, higher than we were before on those. And maybe sorry to tell this, this was not funny. Pomots got their first result, the red ones here, and they were in panic, and they called me and said, Dominic, we have a huge problem in this pool, and jump in a plane and come. And I love to go to Netherlands, but maybe not within 50 minutes. So I asked, I said, are you sure you're backwashing correctly? Yes, we do. There are 2 pumps to backwash the filters. I said, do me a favor. It's not that far away from you. Go and make a video of the side glass. I want to see the backwash process. So 2 hours, they called me and said, Dominic, you were right. And honestly, I love to be right. I really love to be right. Because in the first backwash, the pool operator, he lost a little bit of media, which is good for us and for him. And therefore he said, okay, only the backwash with 1 pump, and even this pump he closed down. So we had a backwash velocity of 20 meters per hour with the old AFM. It didn't do anything. That was not moving, and that's why bam, 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 the values were good the first week, and then brups, they dropped. They changed the backwash regime back to the 2 backwash pumps, backwash at 45 meters per hour, and then you see the values were all good. Then we started the UE, and clearly you see not really a difference in KMNO4, but a reduction of 25% in the combined chlorine. That's what we said. UE does a good job in the combined chlorine. If you would have used medium pressure, probably that would be 0.2. After this stage, we stopped the UV and added carbon. And then you see with the carbon, we got to 0.1, which was definitely the best results. And again, KMNO4 more or less the same. So really 2 learnings on this. UV helps in the combined chlorine, and carbon helps even more. KMNO4 is more or less unchanged. And the second learning, if you don't backwash your filter properly, yeah, it's as I said, it's like a bin. You get more and more solids in it. You have to empty this bin, and you have to empty it completely. So if you operate it the wrong way, it's not good. If you do it the right way, you're smiling. You want to take the time?
Lovely. You can finish this. I'll take the next one.
Okay. He leaves me. I have the sorted. Turbidity. Turbidity, you see, we were before 0.5, and then in average below 0.2. And this is really the target that we want. It's not the best installation, but 0.2 is good. THMs. Let's concentrate on THMs. So remember, chloroform is the main THM, trichloramines. We were here around 50, and then with Daisy, we dropped it to 25 in average. Had an increase with the UV. With the UV, THMs went up. Philip explained before why that happens, because you chop up big molecules and smaller ones, and then you form chloroform. So this is why we are against UV. And then again on the carbon, back to where we have been, roughly between 30 to 25. Trichloramine you have to measure in the air. You pump air for 1 hour through a filter, and then you analyze the filter. Because this is a very volatile product, if you have a lot of movements in the pool, if you have a lot of people, you will have higher values because you move the motor war and it gases more out. But we were here roughly around 500, and then you see here below 250. A little bit of variation, but below 250. So 50% than we had before. And the freshwater, that's the last one. We were here roughly 45 liters per bather, and here in average 20. Let's say 25. So
beautiful. Beautiful. So
Summary.
now,
The summary.
those were a lot
of
of numbers. We put everything on a graph here. That's easy to follow. The 5 key parameters. Number 1, turbidity after installing a daisy was reduced dramatically. That's takeaway number 1. Takeaway number 2, combined chlorine reductions. As we have seen in the numbers, the daisy system was able to take combined chlorine down to 0.4.
This is what we would expect. Without
Exactly.
anything else, it will be around 0.4.
A low pressure UV was able to take it down to 0.3, and then carbon really took it down to 0.1. Then we have THMs, reduction of 50% with daisy compared to sand. Then again, an increase of THMs after turning on the UV, which was to be expected. And then again, a drop to the same level as the daisy after turning off the UV. So carbon has really no impact on THMs.
Maybe a little bit.
Maybe a little bit. Trichloramines, massive reduction of the formation of trichloramines after installing a daisy. That was to be expected. That's 60% reduction. No change with UV. And then here, this is just probably measuring.
If you have a busy pool or not a busy pool. This is just because it's a volatile. You measure it in the air.
Yeah. And then the last one, fresh water use per bather was reduced dramatically again from 45 to about 11 liters.
50%.
50% reduction.
That depends how many bathers you have.
Yep.
You know, they always backwash the same thing. But
Yep.
what you can say, we have half of the disinfection byproducts with half of the fresh water. And that's a factor of 4. So really good.
Okay.
Yep.
So now we get to the, this is, again, you want to say something about this?
That's
we already
skip. We are running out of time.
Yes.
This is what we said. So now we come to advanced oxidation for public pools. And again, this is really, we are the first one in the pool industry who bring this. Philip.
It's really exciting.
Shit. We wanted to start with this.
Okay, let's start with this.
Yeah.
I love this. It looks like Star Wars, in a way. So
what is advanced oxidation?
What is advanced oxidation? You see UV light penetrating the water here, and you have hydrogen peroxide, H2O2, molecules that are being chopped down by the strong UV light into hydroxyl radical, OH radicals. As we have learned earlier, these hydroxyl radicals have a very high oxidation potential, which then destroy and oxidize contaminants, organics in the water. This is what advanced oxidation is.
Yeah.
It is oxidation through hydroxyl radicals.
Exactly. And the way how you produce them, the easiest, there are different ways, but how you produce them in a massive way, you take these photons, very high UV irradiation. Now we go back.
Yep.
It has not updated it. You take very high UV radiation, you know, at 5,000 joule per square meter. I mean, to give you an example, you know, in pools, usually, you know, if you want to disinfect the water, you use about 250. For drinking water, it's 400. Here we have 5,000. This is 12 times more. So we really need a massive amount of photons to split this hydrogen peroxide into hydroxyl radicals. This is what we use the UV for. It's the machine which will split the peroxide H2O2 in I'm lost now.
So
into hydroxyl radicals. And we have talked about this, the most powerful oxidants, short-lived, not like ozone. Ozone can survive minutes. Hydroxyl radicals, just a few seconds.
So hydrogen peroxide is really the precursor. In this case.
Yeah, you need the UV.
Yes.
And you need both.
Yep.
This is the energy who splits this.
Yep.
Yeah. So it has not updated this. So yeah. So this is not a new technology. This is used in water treatment for a couple of years. What is new is, again, our genius boy, Dr. Howard Dryden. He is the first who brought this to the pool industry. He said, Dominic, let's combine this. If we have a daisy system, we have mainly organochloramines. And if we pass just a small amount of this water through advanced oxidation, we will break up all the components which are in this water, and we will solve the problem with combined chlorine. And we partnered up here with Van Remmen. Could be another company, but for us, they are the best. We love them. They are really state-of-the-art manufacturer of low energy consumption UV systems. And yeah, so we partner up with them. This we have seen.
Yeah.
And
so this is where the name Advanox comes from, huh?
Yeah.
From advanced oxidation.
Yeah,
huh?
That's it.
Yep.
Yeah. And here you see how the units are looking like. Now,
so, yeah.
Yeah. You take that?
You have a good example here from the pool in Breitenbach that we have mentioned a few times.
Yeah, this is where I learned to swim, so it's not a new one. And this is our internal test pool here.
Yes. Okay, so what we do is the Advanox is installed in a bypass. Huh? We recommend that you know, the turnover or the water that flows through the Advanox is approximately you know, every 2 to 3 days. Huh?
Yeah. So you only go in this bypass. You take all the water that you have in the pool every 2 to 3 days through the Advanox system.
Yeah. So this is roughly, you know, your pool volume divided by 60 hours. In this case, is 3 meter cubes per hour. That's our flow through the bypass here. Huh?
60. That's 2.5 days. 48 is every 2 days. 72 is every 3 days.
Yep.
Very complicated.
Yeah. Yeah.
So I use the 60 as the, and then you have the 180 cubic meters divided by 60 hours gives you 3 cubic meters per hour. And you do ideally this with a bypass pump. So you always have the same flow. You dose with our flocculation pump, small amount of peroxide just in front of the bypass pump. Use a small flow bead to control the flow.
Yeah.
Job done.
Very simple, huh?
Yeah. Why only, Philip? Why only every 2 to 3 days? Why is this enough?
Well, the inorganic chloramines, they build up very quickly, but the organic chloramines, they build up relatively slow.
Yes.
Huh? So you don't need to treat the whole pool water, you know, in a short time. You have more time, basically.
You have more time.
You have more
they
time.
build up over 3, 4, 5, 6 days.
Yeah.
And it depends how much you want to reduce them. You can treat it in a full stream, but that will be quite costly. So that's okay. And because in the Daisy, we don't have, or we have a very low amount of inorganic combined chlorine. Our problem is the organochloramine. This is why every 2 to 3 days is good enough.
Yep.
So this is the key one. Organochloramines are building up slowly. Every 2 to 3 days is enough. And the dosage of peroxide?
That depends a little bit on the concentration of the peroxide, right? I think here in Switzerland, we still have 35% concentration.
Yeah, but in Germany and
it's a bit
in these other paranoid countries, it's not paranoid countries, it's paranoid governments, you know, because of terrorism. This was before we had the virus, it was terrorism. They said you can build bombs with hydrogen peroxide in this concentration. So this is why it's only allowed 12%.
Okay.
Completely stupid. But your dose rate is 10 milliliter per cubic meters of water that you go in the bypass. So Breitenbach, 33 cubic meters per hour, multiplied with 10 milliliters, that's 30 milliliters of the higher concentration. If you would have 50%, you can reduce it. You also will see, you know, you will enter the Advanox with a certain concentration, let's say 10 ppm, and exit of the Advanox, you will have lost peroxide, roughly 20, 30%. So you go in with 10 ppm, you go out with 8 ppm. And this is forming these free radicals. What do you want me to tell you this?
Well, you know, let's look into the inside of the Advanox. You can see here these fins. It's like a spiral, a spiral around with the lamp in between, and the
looks like a CPM.
In a way, right?
Mixer.
So the purpose of this is to make sure the water gets as close as possible to the lamp, because the closer to the lamp, the stronger the UV radiation is.
So we do not use a normal one, a special one, specially developed for this process by our friends from Bremen, that you really bring the water always as close as possible to the lamp.
Yep.
So this is why there is a special chamber, because then you have higher UV radiation, then you have more effect in splitting this. Here you see the results. I leave this quickly to you. I'm back in 1 minute.
Okay, good. So the results of Breitenbach pool. You see the green line, the free chlorine, which is less relevant for this, but the red line is our DAISY combined chlorine level just below, you know, a 0.4 ppm. After changing over to DAISY and Advanox, you can see that the combined chlorine level dropped to actually an average of less than 0.1. So this is the desired result. This is the proof that by adding the Advanox, we are able to get the combined chlorine level down to 0.1, or in this case, actually even a little bit less. One other big advantage that we get with the use of Advanox is that Advanox is very effective at reducing pharmaceuticals and personal healthcare products. It's able to destroy them and break them down. This is what we see here. We have tested Advanox in two ways. We first started testing Advanox with ACO only. So no peroxide, only ACO, to see what it would do. You can see this in the orange bars. So it is able to take out or reduce a number of these chemicals. Don't ask me to pronounce these chemicals here, please, because I'm not able to do that. But what you can see also here clearly is that the use of peroxide was very strong. I mean, we basically have 100% performance of peroxide in combination with Advanox in the reduction or removal of these pharmaceuticals and personal healthcare products. Okay. So this concludes this. Let's summarize again.
Yeah, did you miss me?
Do you want me to continue? No.
Okay, I take maybe the first part.
Yep.
You know, why is Advanox so much better than medium pressure? And it's really about the THMs. This is why we are against medium pressure.
Yep.
It also doesn't consume any chlorine, you know, like the medium pressure, but it's really about the THMs. You just be clear, you only treat a side stream, and we do not use UV for disinfecting it. We are using UV to generate these free radicals for this advanced oxidation. But in this process, also, if you compare it from the cost, you know, it's much cheaper.
Yep.
Much cheaper in investment, and especially much cheaper in operation cost. You know,
Clearly.
Because our lamp has the big one, 600 watts. You know, where you would to treat a 500 cubic meter pool, where you would need a 6 kilowatt UV medium pressure. So 10 times, at least 5 times to 10 times less of energy consumption.
Massive, huh? And there's also clear advantages of Advanox versus AFM.
Yeah, but maybe two more things. More heat, you know, if you have medium pressure generates more heat so that the lamp gets warmer, and therefore you have more problems with scaling of calcium. And the lifetime is shorter. It's roughly 8,000 hours, where Advanox 12,000. Maybe you could operate it to 69,000 hours, but think on our families, you know, maybe change it every 12,000 hours. Then you're on the safe side and you generate a little bit of turnover for us.
Yeah. Okay. Yeah.
So that's
good point. Yeah. Those make big differences. Now, if you compare it with AFM and activated carbon, certainly an advantage is we have no loss of chlorine, which we have with carbon, obviously. We also know that with carbon, we can create some black dust, which requires a rinsing phase, for example, after backwash.
Yeah, that's important. You know, if you have carbon, really, usually I say in a pool, you don't need rinsing, you know, with Pesco. But yeah, here I would add a rinsing valve that you can avoid this. And last but not least, you know, if you don't have a flat filter bed, you know, because your top diffusers are not well designed, then you have a problem. So I love this solution with carbon. It's the cheapest. I think it's a very good one, but Advanox is it's one step bigger, better.
Yes.
Yeah.
So it is much healthier, much better than a UV system.
Yeah. We really believe on the left side, you see Advanox. We believe that's the best solution. And if you compare this with other systems, with the UV system, it's by far better. I mean, there is no question. And even if you take it with an ozonizated system, we think it's as good, maybe even a little bit better than an ozone system, but at much less cost, much less cost. So it's great. Like Trump would say, it's so good.
Yeah. So how much does it cost?
Oh yeah, here you see about the cost. Well, that's indicative. These are list prices. You know, we have here the AOP 80 for pools up to 80 cubic meter. Under us, you can go with this unit also bigger, up to 120. And then you have for the 250 and for the 500 cubic meter pool, you know, you're below 10,000 euros. You need a small flocculation pump to dose the peroxide and the flowies, and an extra pump, you know, that you have a bypass pump. I have chosen here the spec variable speed. You would not need this. You just go for the smallest measuring pump, and then the cost here are 300 euros. So it's nothing. And also you see the replacement of the lamps, you know, once per year or every 1.5 years. You know, it's not really high cost. So cost-wise, it's not big. Yeah. Summary, it's the best. It's the very best.
Yes. Right, so Daisy reduces oxidation demand.
This is important here.
Very important, reduces THMs and reduces overall inorganic chloramines. That's the key, right? Yeah. So why do we need the Advanox? We need the Advanox because that is capable of reducing organic chloramines, leading to an overall lower total combined chlorine.
That's it. And according to our knowledge, it's very new. You know, we just get now the first units. The test we have done with 2 demo units. We just get them next week, I guess. You know, according to what we know today, it's the very, very best. Most of our international partners have ordered 1 unit as a special price and want to go to the market and try it out. So really try it out. Maybe in 12 months we have more information. We have more data. According to all our tests, it's very good. It's the best. Yeah.
Great.
Very good.
Okay.
So in a week, pathogens. So today we spoke about chemical reactions. Next week we talk about biology again. You know, and that's the last one before we come then to the test and to the summary.
So about all